love playing. That's why I'm going to recreation first. I just want to Leslie know the Recreation and Parks Association.
So you want 2 months.
Then it would end up being NPRI. I don't know how much.
Pardon? How to bond? Push. Push harder.
How are you? I'm great because I'm leaving today and not coming back. I'm going to sounds like it probably is, but last year I learned to make cool programs for people at every age 6.
All right, well, everybody's here, so I'm going to go ahead and get started. So what were we talking about last time? Naming, right? Naming alkanes. What are the rules, the 3 rules to naming alkanes? The 3 overall rules. Huh? We're going to find the longest chain. That becomes our parent, right? And if I have 8 carbons in the longest chain, it would be a what? Octane. 10? 4? All right, good enough. Then what do we do once we've identified the longest chain?
We find
The substituents, okay? That's right. And the easy way to do that, right, is to circle that longest chain. And everything that's inside the circle belongs to the parent. Everything that's on the outside is a substituent of some sort, right? You'll notice in organic chemistry there's a lot of circling going on, right? And then once we've identified the substituents, we have to figure out what they are, right? So if I have a CH3 substituent, what would that be? How would we name that? Methyl. If I had a CH3, CH2, it would be a... Okay, so basically it's the alkane minus a hydrogen makes it a YL, right? An IL group. Okay, so that becomes a substituent. And then we got to number the thing, right? And how do we number? Left to right or right to left?
The least number.
Okay, so there's several rules, but one of the first ones is where we come to that first substituent, right? All right, very good. So we can number left to right, right to left, up and down, ziggy, zaggy, it doesn't matter. We have some rules to follow to determine the numbering system, right? But ultimately, we really want to give our substituents the lowest possible numbering system, right? And so when we're naming, if we have 4 methyl groups, how would we name that? Would we say methyl, 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 methyl?
trimethyl.
If we have 4? Tetra. Yeah, so if we had 4 methyl groups in our longest chain, we'd call it a tetramethyl whatever, right? And we separate numbers by what? We separate numbers by commas. So if it was 1, 2, 3, 4 tetramethyl, it'd be 1, 2, 3, 4 dash. But numbers and letters are separated by dashes, right? So today we're going to continue on a little bit of nomenclature. We're going to talk about how we name cycloalkanes. We started on this a little bit. And then we're going to talk about how we can rotate around sigma bonds. We're going to talk about Newman projections and this concept of conformational analysis, which actually turns out to be very, very important overall. Okay? So when we're talking about the nomenclature of cyclic alkanes, right, the same rules apply, except we're going to insert this cyclo part right in front of the parent, right, to signify that it's a cyclic alkane. So for example, here we recognize that we have a 6-carbon ring, and 6 carbons belongs to hexane, right? But since it's in a ring, it becomes cyclohexane. Is that a saturated or an unsaturated molecule?
Unsaturated.
And why? Excuse me? I'm sorry.
It has spots to bond in, right?
Well, we have to remove 2 hydrogens to make the ring, right? And so what's a unit of unsaturation? It's H2 equivalent, yeah, or hydrogen, molecular hydrogen equivalent, or 2 H's, if you will. Okay? So yes, cyclohexane in and of itself is unsaturated by 1 unit of unsaturation. Okay? So we talked a little bit about this, right? This is methyl cyclohexane. Why is this not 1-methyl cyclohexane? Because it doesn't matter? Why doesn't it matter?
Because there's only one.
That's right. There's only one group. So no matter where Nathan puts it, it's always going to be position 1, right? So that's right. So we don't have to worry about the number in that particular name. Here, we've got this funny looking substituent, and that's called a tert-butyl group. And I always remember because it looks like a T, right? Why butyl? Because there's 4 carbons, right? So that's a tert-butyl group. And so that becomes tert-butyl cyclopentane. Notice tert is italicized, okay? So that is tert-butyl cyclopentane. Now, if we have more than one substituent, numbers start to matter, right? If Matthew puts on 2 methyl groups, for example, on a cyclohexane ring, it matters. You can't just say dimethyl cyclohexane, because we could have 1,1 dimethyl cyclohexane, we could have 1,2 dimethyl cyclohexane, we could have 1,3 dimethyl cyclohexane, and all of those are unique compounds, right? And so we have to number, okay? And so we can number within the ring, either going in a clockwise fashion or a counterclockwise fashion, okay? And we're always going to number such that the substituents get the lowest possible numbering. So in this particular case, it's going to be numbered clockwise, not counterclockwise, because 1,3 gives lower numbers than does 1,5. Okay, so 1,3 dimethyl cyclohexane and 1,5 dimethyl cyclohexane are actually the same molecule, but the one's named incorrectly. Okay, and it turns out that it's the one on the right that's named incorrectly in this particular case. Are there any questions about that? Pretty straightforward. Yes, ma'am.
When you're going from a name to a structure, how do you know to go clockwise or counterclockwise?
Well, if I look at the name 1,3-dimethyl cyclohexane, how would you go about approaching that problem? I would start off with the parent, and I know it's going to be a cyclohexane, right? And I know that I'm going to have a methyl group on positions 1 and 2, right? Or excuse me, 1 and 3. So I'm going to, in that case, it doesn't matter whether you go clockwise or counterclockwise, just as long as you put 1 methyl on carbon number 1 and 1 on carbon number 3. You'll have exactly the same thing. Okay, so, for example, so if we look at this, I have my cyclohexane, and so if I number, or if I number like this, there's 1,3, there's 1,3. And if I built the models of both of those, I'd find out that in fact they are identical. Okay? So it doesn't matter when you're trying to reconstruct, because you're going to end up putting those methyl groups where they belong. Does that make sense? Okay. All right. When we have 2 different substituents, however, in the previous example, both substituents were methyl. Okay? With 2 different substituents, you're going to number the ring to assign the lower number to the substituents alphabetically. Here it doesn't matter. Methyl and methyl are identical, right? So methyl is always going to have position 1. But in this particular case, where we have a methyl group and an ethyl group, you have to decide which one is going to take priority. And you follow alphabet. E comes before M in the alphabet, so you want your ethyl group to be position 1. Then you will determine whether you go clockwise or counterclockwise. Okay? Well, what happens if we have a ring that has a long chain associated with it? How do we name it? Well, it depends. Okay? If the ring has more carbons than the chain, you're going to name it as an alkyl substituted cycloalkane. If, however, the chain is longer than, has more carbons, that is, than the ring has carbons, then you're going to name it as a cycloalkyl substituted alkane. Okay, and so here's some examples. I've got a ring and I've got a chain, right? How many carbons do I have in the ring? Got 6. How many do I have in the chain? 4. So it is a butyl cyclohexane. Okay? We would call that butyl cyclohexane. Okay? No number. Why no number? Only one substituent on there. That's right. Now, if I look at this, I notice that I've got 4 carbons in the ring, so that's a cyclobutane, right? But I've got 6 carbons in the chain. So I'm going to name this as a cyclobutyl substituted alkane. And so this becomes 1-cyclobutyl hexane. Okay? Why do I have to have the 1 there?
Because it matters.
It matters, and it matters a lot, right? Because 1-cyclobutyl hexane and 2-cyclobutyl hexane are what are, with respect to one another? Stereoisomers?
No, constitutional.
They are constitutional isomers, that's right. And we'll learn about all these other isomers, okay? They can get kind of jumbled up. But in fact, they are constitutional isomers of one another. How about 3 in the 3 position? If we put the cyclobutyl in the 3 position, would that be different than the other 2? Absolutely. There are some common names that you need to know about. And these have no real rhyme or reason other than this, they take this shape. All right? So when we have a cube, these 4 carbons all connected together up here, these 4 connected down here, and make a nice cube out of it, we call that cubane. What's odd about cubane?
It's 3-dimensional.
It is 3-dimensional. What else? Pardon?
It's got 90-degree bonds.
But what's the hybridization?
SP3.
sp3, and the bond angles want to be what?
If it's SP3, then it would be 1.5.
Exactly, and they're 90 degrees. So would you predict that this would be a stable molecule or an unstable molecule? It is an unstable molecule. However, it can be made. And the military had huge interest in this about 20 years ago, maybe 25 years ago. Can anybody tell me why? Explosives. That's exactly right. These cubane molecules were thought to be good explosives. Turns out they're too hard to make practical explosives with. But nonetheless, they got interested in this. Houseane, right? Kind of looks like a little house, right? Doesn't have a door or windows, but it kind of has the outline of a house, right? Churchane, you know, you've got what looks like a house and a steeple, right? So we call that churchane. And then, of course, basketane. Looks like a little basket that you might carry your Easter eggs in, right? So you can have cubane, houseane, churchane, basketane. I just want you to know that there are some structures out there that take on the name of what they look like. I don't expect you to be able to name complex structures with them. But I would expect on an exam, if I gave churchane, that you'd be able to recognize that that's churchane. Okay? And it really looks like churchane if you put a T-butyl group up here. So some people will do that. Okay. Any questions about that? All right. Now we have to be mindful of the fact that life isn't always as simple as having one ring. And sometimes we can have more than one ring in a molecule. And we call these bicyclic compounds when we have 2 rings. Okay? Can you tell me why that molecule has only 2 rings. Because I thought our definition last time was a ring was if I start at some point and I go around without ever lifting my pencil, that's a ring, right? Well, there's a ring. Is that not a ring? And is that not a ring? It looks like there's 3 rings. But in fact, there are only 2 rings. And it's because it only takes 2 disconnections to get it to be acyclic. Okay, so if I build a model of this, how many carbons do I need? So I've got 4 already made. There's 5. There's 6. And there's 7. So I'm going to connect 6 carbons together to form a ring. My model kit's kind of falling apart. I've abused it for a number of years. There's 1 ring. Now how do I make the other part? What do I do with this carbon? Stick it in the middle? So I got to connect it, right? And so that is a flat representation of that. And you can kind of see it projected onto the screen. Feels like it has a gap. Right there on the back. Yeah. But notice, if I use my finger, it looks like there are 3 rings. But in fact, there are only 2 because it just takes this disconnection and that disconnection to get a completely open system. So it's how many times you have to disconnect tells you how many rings you have. Okay? So this is a bicyclic compound, bicyclic alkane. Okay? And so the number of rings are going to be equal to the number of disconnections when you build your model. Some people will use their eraser on an exam. They'll draw it out and then erase to see how many disconnections it takes. Both work fine, but I think a model kit works better overall. Okay? And so we have what are known as the bridgeheads and the bridges. Define a bridgehead for me other than the fact that it's red.
It's one that is triply bonded to carbons.
Okay, that's true. It's bound to 3 other carbons. What else? That's a good way to point it out. What else? It connects all the bridges, doesn't it? All the bridges are connected. So I've got a 2-carbon bridge, a 2-carbon bridge, and a 1-carbon bridge in this particular molecule. And this is how you would draw it on a flat piece of paper. You would draw the ring, and then kind of go off at an angle to the 1-carbon bridgehead, and then back down to the other, or to the bridge, and then back down to the bridgehead. Okay? Now, we have to figure out how to name that thing. Okay? Bicyclic compounds are named by first counting the total number of carbons in the bicyclic ring. Okay? The base name is the alkane name for the total number of carbons with the prefix bicyclo. Okay? So, how many total carbons do I have there? 7. So this is going to be a bicyclo, right? Heptane. Notice there is a space in between them. And in that space, we're going to put the number of carbons in the bridges. Okay? I have a 2-carbon bridge, a 2-carbon bridge, and a 1-carbon bridge. So in brackets between this are going to go those numbers. Whoops. Sorry about that. It's going to be bicyclo 2.2.1 heptane. We go from the highest number to the lowest number. In this case, since 2 is used for both bridges, it's 2.2.1. So bicyclo 221 heptane. It tells us I've got 7 total carbons in the ring system. The bridges are drawn, and then you put a 2-carbon bridge, a 2-carbon bridge, and a 1-carbon bridge. That's how you would draw that. Okay? What do you notice about the numbers in here? If you added them up, what are they?
Where did those numbers come from?
That's the numbers of carbons in the bridges. I have a 2-carbon bridge, a 2-carbon bridge, and a 1-carbon bridge. So bicycloheptane, that just tells me I've got a bicyclic compound with 7 carbons. Doesn't tell me how they're all connected, does it? But the 2,2,1 does. And notice if I add these up, it's always 2 less than the total number of carbons. Why is that? Because the bridge heads don't get counted. That's right. It's the bridges that we're counting in there. So if your numbers don't add up to 2 less than the total number in the parent, you've done something wrong. It's a way for you to check yourself. Okay? So now let's look about sigma bonds and pi bonds. So I want you to build a model of an alkane and an alkene. So let's make it simple. Make ethane and ethene. So there's ethane, and there's ethene. So to make the ethane, you just need 4 of the sp3 hybridized carbon pieces. And to make ethene, you need the double bond part and then the 2 gray sp2 hybridized carbons. And I'm just going to put a couple of spheres on mine, so you don't have to do that. But no. You need that one right there. And pull them in tighter, they'll come apart.
Like how about one shade of colors? Like I can't really see that.
That's okay. Everybody got their part together? All right. So what can you tell me about the alkane? If we look at the alkane, what can you tell me about the hybridization, for example? It's sp3, right? And notice I've put on a red sphere and a blue sphere just to mark some positions. But what can I do about these 2 carbons? I can easily rotate around them. Why is that? Why can I do that? I'm not breaking any bonds, am I? And what else? Well, it does require some energy, and we're going to see that in a minute. It doesn't require much, I'll give you that. But why can I freely rotate around that? Why is it that I'm not breaking any bonds? Okay, that's true, but why? It doesn't break, but why?
Electrons aren't shared besides the 2 atoms there.
Okay, but what else? What about the symmetry of the bond? It's like a cylinder. If you looked at a cross-section of it, it's a cylinder, right? It's bound only by one point, and so I can rotate around the center hub. It's kind of like my wheel on an axle, right? I can rotate around that. That's how you got here this morning. Your wheel, right? You want to think of this as the wheel, is on an axle, single axle. They do not put 2 axles to your tire. Why is that? It won't turn, right? Basic physics, okay? However, if I look at my alkene that I built, what do I notice? What's the hybridization? sp2. And so I have how many sp2 orbitals? On each carbon, I've got 3, right? So I've got an sp2 here, an sp2 here. There's an sp2 connecting the 2 carbons together. And then on each carbon atom, there's what? An unhybridized p orbital that bonds with each other to form the pi bond, right? And so I've got two bonds between this carbon and this carbon, which is sort of modeled by this double bond piece. Can I freely rotate around that? No. So this blue sphere and this red sphere are always going to be what we say are trans to one another on opposite sides of this plane, right? And so if I want to put the blue sphere over here, I can't do that. Notice what I'm doing to my bond. Does that look good? No. And don't do it to your model, all right? My model's been abused enough, okay? So to go from this to this is not a simple rotation. And in fact, this and this are different molecules. This will have different boiling points than the other and so on and so forth. Is this and this really different molecules? No, there's free rotation. Okay? Does that mean that this and this are of the same energy? No. And in fact, they are of very different energy, and we're going to learn about that today as well. Okay. So we just talked about the rotation. We can rotate around sigma bonds because they are cylindrically symmetrical. Okay? It is the same thing as your tire on an axle. You can rotate around that axle. Okay? Not a problem. Put a second axle on your tire, you're not going anywhere, right? That's like putting a boot on your tire when they go out and, you know, you parked wrong and they put that yellow boot on your car. Anybody ever have that happen to them? You're not going very far, right? Because you basically have a second axle around that tire and you just can't move, okay? Now, going from one position to another by rotating around a single bond, that's called a conformer, okay? So this is a different conformer than that or that. So how many conformers do I have for this simple ethane molecule? I have an infinite number, right? Just depends on how small an increment that I want to move it each time, right? But in reality, there's only a handful of conformers that I really need to pay attention to. Okay? So do you all think that that is exactly the same energy as that? Which one do you think is higher? That one or that one? You think that one's higher or lower in energy than that one?
That's it.
I think this one's higher because this one are kind of close together and I don't know if they want to do that.
Okay, repeat that please.
I said I think this one's higher because in this one they're kind of close together and I don't know if they should go about it.
Okay, you've got the right answer. These are closer together. So is that going to be higher in energy or lower in energy? If I take two people and I try to shove you into the same space, are you going to be happy or not so happy? Not so happy, right? You want to have your space, right? So this is actually going to be more stable, so it'll be lower in energy, right? Because these get further apart. Getting things closer together is actually a bad thing, okay? So this brings us to Newman projections. How do we draw these different conformers that are three-dimensional on a two-dimensional surface, a piece of paper or a computer screen? We use what's known as a Newman projection. What do we mean by projection? Pardon?
It sticks out.
Okay. What do you think of when you hear the word projector? You think of something like that, right? Now, if you have a nice, bright, sunny day, you can actually make a Newman projection. This is a Newman projection. We are looking down the carbon-carbon bond of interest. Okay? And what we are doing is projecting that image onto a two-dimensional surface. So this is the front carbon. This one back here is the back carbon. Okay? And what you'll recognize if I hold that up, if I can hold it up just right. That's a Newman projection. Okay? But we have to have a way to represent that. And so the way that we represent that, when I'm holding the carbon-carbon bond that I'm interested in, the carbon that is away from me, we represent as a big circle. That means it's away from me. The carbon that's closest to me is a little dot. Okay? So the dot represents the carbon that's in front. The big circle represents the carbon that's in the back. Okay? So how do I represent that carbon-carbon bond? I don't. It's the projection. Right? So if I look at the projection again, you'll see that you don't see that carbon-carbon bond because that's what you're looking down. You assume that this little dot and this big circle are actually bound together by a sigma bond. Okay? So that's there. So now what do we have to do? We've got the two carbons. We've got to put everything that's connected to those two carbons on those carbons, right? In this case, since it's ethane, what's on the carbons? Hydrogens, right? So what we do is we draw a line to the back carbon and we stop at the circle. So this is a carbon, this is the carbon, this is a hydrogen, this is a hydrogen, and this is a hydrogen when we put the hydrogens in. And that tells me that those hydrogens are bound only to the back carbon. Notice, however, for the front carbon, we draw through the circle and go to the point. That does not mean, let me repeat this, that does not mean that this carbon is bound to the back carbon and the hydrogen. There is no bond there. That's the consequence of a projection. Okay? Because we're taking a three-dimensional thing and smashing it into a two-dimensional surface. In fact, you can take your model and imagine smashing it flat onto that two-dimensional surface to get a Newman projection. Okay? If you have a big enough model kit like one of them that I've got, you can actually go out on a nice bright sunny day and you can make Newman projections on the sidewalk with the sun. And you can put all kinds of things on them and see what you got. Field trip? They have to have a sunny day. Yeah, maybe we could do that. Okay? Now, let me, instead of just two carbons, now we're going to look at butane. So there's butane. C4H what? How many hydrogens do I have?
2, 4, and 6.
That's right, I got 10, right? C4H10. I can technically look down the carbon 1, carbon 2 bond and get Newman projections. I can look down the 2, carbon 3 bond and get Newman projections. What am I looking at here? The 1, 2 or the 2, 3? What am I looking at here? Here's my Newman projection. Am I looking down the 1, 2 or the 2, 3? I'm looking down the 2, 3. Okay, so there's my Newman projection. Let's see if I can get it. Okay, there's my Newman projection that I'm looking at. Okay, so there's my back carbon, and attached to that back carbon is a what group? A methyl group and 2 hydrogens. Here's my front carbon connected to 2 hydrogens and a methyl group. Okay? We call this a staggered, because if I look down that carbon-carbon bond, everything looks staggered to me. But it's also called anti, because this group and this group are 180 degrees away from each other. So when I look at the Newman projection, I ask myself, what's the big group? This is big, these are small, right? So big and big are 180 degrees to one another. That's anti. Now I can rotate around this carbon-carbon bond, right? So as I start to rotate, we end up, if I rotate 60 degrees, now I have a different Newman projection. I have that one. What does it look like? Everything's eclipsing itself, right? These hydrogens are eclipsing each other. This hydrogen and this methyl group are eclipsing. This hydrogen and this methyl group are eclipsing. Is that good or bad? Okay. It is bad. These things are starting to occupy the same space. This little hydrogen and this big methyl group are starting to get in the same side of one another. Not good. But as I start to rotate it a little bit more, what happens? Better or worse?
Worse.
Better or worse than that? A little better. Because now things are staggered again. Staggered's good. Okay? Now what happens is I continue to rotate a little bit more. I start to get eclipsed, and now I've got two big things eclipsing. Is that better or worse than this eclipsing? That's the actual worst. That's right. It's the highest energy. Okay? And we call that methyl-methyl eclipse. Big groups are methyl-methyl eclipse. Okay? When we're here, we call this the gauche conformation. Can anybody tell me why we call it gauche? If you look up the definition of gauche in the dictionary, you'll find that the first definition is socially awkward. Not the reason. But you'll find like definition 3 means non-planar. Here's a plane, and here's a plane. The methyl groups do not lie in the same plane. Here they lie in the same plane. Here they do not. Okay, and so we call that the gauche conformation. It is not because it's socially awkward. Okay? So, we can continue to rotate and finally get back to our starting point. Okay? This is called conformational analysis. And you need to be able to look at a conformation and determine whether or not it's relatively high in energy, kind of intermediate, or relatively low in energy. And again, the only way you're going to be good at it is to practice. Okay? But always remember, you want to keep the big groups on the 2 carbons in the Newman projection as far apart as possible for the lowest energy conformation. And staggered is always better than eclipsed. Those are the things that you've got to keep in mind. Okay? So I'm going to go ahead and cancel my